Mathematics, Probability, Part 2, Conditional Probability. Let A and B be two events of the universe omega. The event B, knowing A, is the event denoted by B/A. It is read B knowing that A, or B such that A, or B given that A. There is a reduced sample space A. To calculate the probability of event B such that A, probability of event B in reduced sample space A, we use the following formula. Probability of B knowing that A equals probability of A intersection B over probability of A, where definitely probability of A is different from 0. We can also define probability of A knowing that B, which is equal to probability of A intersection B over probability of B, where B is different from 0. Probability of B is different from 0. Now we can look at this figure. Omega is representing the whole sample space, and we have two events, B and A. Event B, it has a complementary event B bar. Event A, it's drawn in the green oval. We have the intersection between A and B, colored blue, intersection of A and B bar, colored yellow. So to calculate the probability of B, knowing that A, it's the probability of A intersection B over the probability of A. We can also calculate the probability of B bar, knowing that A, so it's the probability of A intersection B bar over the probability of A. Properties. Let A and B are two events in the sample space omega. Probability of B knowing that A equals probability of A intersection B over probability of A. Probability of B bar knowing that A equals probability of A intersection B bar over probability of A. We can also calculate, and we need to know, the addition of probability of A knowing that B and probability of B bar knowing that A, which is equal to 1. And here is the proof. Probability of B knowing that A plus probability of B bar knowing that A, it's equal to the sum of the ratios probability of A intersection B over probability of A plus probability of A intersection B bar over probability of A. From the previous figure, we can add the numerators to have probability of A intersection B plus probability of A intersection B bar, its probability of A, divided by the common denominator probability of A, which is equal to 1. Also, we can calculate probability of B bar knowing that A, it's 1 minus probability of B knowing that A. So the last property, it's derived from the third property, that we can take one unknown to the other side of the equation. Now, tree diagram. Now we can represent some probability problems using a tree diagram. The sample space, it can be divided into two reduced sample spaces A and A bar, and these two sample spaces, they can have probabilities, so we're gonna represent them by two branches. The first branch, probability of A for the event A, probability of A bar for the event A bar. Similarly, another event, which is event B, in the reduced sample space A, we have a branch where we have to write the probability of B knowing that A for the event B in the reduced sample space A. Another branch, probability of B bar knowing that A for the event B bar in the reduced sample space A. We can also write the probability of B knowing that A bar for the event B in the reduced sample space A bar, probability of B bar knowing that A bar for the event B bar in the reduced sample space A bar. Sometimes we need to calculate the probabilities of A intersection B, so we have to go by multiplying probability of B knowing that A times probability of A. So we have to multiply the probabilities in these two branches. Probability of B knowing that A times probability of A. Now to calculate the probability of A intersection B bar, so it's probability of B bar knowing that A times probability of A. So to calculate probability of A intersection B bar, it's probability of B bar knowing that A times probability of A. So we have to multiply the probability in this branch by the probability in the first branch, written in the first branch. Now to calculate the probability of A bar intersection B, so we have to calculate the probability of A bar intersection B. It's probability of B knowing that A bar times probability of A bar. So we multiply the probabilities on these two branches. Similarly, we can calculate probability of A bar intersection B bar, which is probability of B bar knowing that A bar times probability of A bar. So we multiply the probabilities in these two branches. Now here there's an example. Rami store sells t-shirts and jackets of two different sizes, small and large. 70% of the articles are t-shirts, 30% of the articles are jackets, 40% of the t-shirts are of small size, 50% of the jackets are of the large size. A client chooses randomly an article from the store. Consider the following events. T, the chosen article is a t-shirt. J, the chosen article is a jacket. S, the chosen article is of the small size. Now, we are going to represent this in a tree diagram. So step number 1, it's translated by probability of T, 70%, 70 over 100, 0.7. Statement number 2, it's translated by probability of J, 30 over 100, which is 0.3. Statement number 3, it's translated by small item chosen from the t-shirts, 40 over 100, 0.4. Statement number 4, it's translated by large item is chosen from the jackets, so 50 over 100, 0.5. So here is the tree diagram. The sample space, it is represented by T and J. T to represent choosing an article from the t-shirts, J to represent an article chosen from the jackets. Here we have the probability of T, which is 0.7, and probability of choosing a jacket 0.3. Now from the jackets we have either small size jackets, t-shirts, sorry, and large type t-shirts. This is the probability of small items chosen from the t-shirts, and this is the probability to choose a large sized t-shirt. And similarly, here we have a small sized jacket, and here we have a large sized jacket. Now this is a more explanation. 0.7 represents probability of T, 0.3 probability of J, 0.4 is small, knowing that it's a t-shirt, 0.6 large, knowing that it's a t-shirt, 0.5 for the first branch, small, knowing that it's a jacket, 0.4 large, knowing it's jacket. Now we need to know that the sum of the probabilities on the two branches, it should be equal to 1. Now sometimes we need to calculate probability of S intersection T, which means a small item that is jacket. So we can do this by multiplying probability of t-shirt. Sorry, we have to calculate probability of S intersection T. We have to multiply probability of T by probability of S, knowing that T, which is 0.7 times 0.4, which is 0.28. To calculate probability of a small item, it can be a small item and a t-shirt or a small item and a jacket. This will be translated by probability of S equal probability of S intersection T plus probability of S intersection J. We can use the tree diagram to calculate probability of S intersection J by the same way we have calculated probability of S intersection T. So probability of S, it's probability of S intersection T plus probability of S intersection J, which is 0.28, plus probability of J times probability of S, knowing that it's J, which is 0.28 plus 0.3 times 0.5. 0.28 plus 0.15 is 0.43. Thank you.